We are starting with, this will be slide number 66. And it's our last section in slide set 2A, chapter 2A. This section is on chemical equations or chemical reactions. In chemical equations, we have the substances that react or that enter into the reaction. On the left of the arrow are called the reactants. And then the substances that are produced are the products, and they are on the right of the arrow in most equations. So when you see compounds, or the molecular formula for a compound, make sure you know what it means. H2O is the molecular formula for water, and it means that one molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. 1 molecule of glucose, C6H12O6, contains 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen, for a total of 24 atoms. So it's a much larger molecule than water is. And then for the types of chemical reactions, we have synthesis reactions, which are referred to as anabolism in the body. All of the synthesis reactions would be called anabolism. This synthesis reaction is representing amino acids, which are the building blocks of proteins. Amino acids being combined into a chain to form a polypeptide or a protein. That's an example of a synthesis reaction. Some proteins are enzymes, some are hormones, and some are structural proteins like collagen, and some are for protection like keratin. There's a lot of our body is made up of many, many proteins. Then we have breakdown reactions, which are altogether known as catabolism or catabolic reactions. And another word for breakdown reactions is decomposition or dehydration synthesis. And an example of that would be this long molecule, this long polymer called glycogen, which is found in our liver cells, can be broken down into individual glucose molecules, and then the glucose released into our blood to raise our blood sugar when our blood sugar is low. So that is an example of a decomposition reaction. Then we have exchange reactions that occur that I'm not going to focus on that much. And I'm sorry, this looks weird. Let me, I don't want to stop recording, but I think I can fix this. There we go. Sorry about that. All right. So we also have redox reactions or oxidation reduction reactions. And that means that in these reactions, one of the reactants is reduced and one is oxidized. So if we look down here at this is a reaction that occurs in our cells to form ATP. It is called cellular respiration. So our cells take glucose, which comes from any carbohydrate that we eat is converted to glucose. Glucose and oxygen together are the reactants for cellular respiration, and the products are carbon dioxide and water, and ATP, which is the molecule that we use for energy. All right, so glucose has 12 hydrogen atoms. And those hydrogen atoms contain protons and electrons, but we're going to focus on the electrons because what do we see happen to this glucose is that it loses those hydrogens. It becomes carbon dioxide. And when it's a reactant, it has carbon, oxygen, and hydrogen. But when it becomes a product, it loses the hydrogen and only has carbon and oxygen. Okay, so when it loses those hydrogen atoms, it is losing 12 electrons, and loss of electrons is oxidation. So what we say is that glucose is oxidized, And it is because we see the loss of that hydrogen from glucose, okay? Glucose is oxidized because oxidation is loss of electrons. We can represent that with this oil. Oxidation is loss. Oxidation is loss of hydrogen atoms and electrons, okay? And then the other part of that is one of the reactants is going to be reduced, and it's going to gain electrons. Reduction is gain in redox reactions. So this oxygen is going to gain hydrogen and become water, and the electrons are found in those hydrogen atoms. So we say that the oxygen molecule is reduced because Rig, R-I-G. Reduction is gain, okay? Oil, Rig. Oxidation is loss, reduction is gain, and that means loss of electrons that are found in hydrogen atoms. So if you look at a chemical, at a compound, and it loses hydrogen as a product, then it's oxidized. And if you look at one like oxygen and it gains hydrogen, it's reduced because the electrons are found in those hydrogen atoms. So oil rig, oxidation is loss of hydrogen atoms and their electrons. Reduction is gain of hydrogen atoms and their electrons. Some reactions are exergonic. Most of our breakdown reactions are exergonic. So catabolic and oxidative reactions typically give off energy, and they're exergonic. And then our anabolic reactions or synthesis reactions tend to require energy, so they are endergonic. Some reactions are reversible, particularly our buffer reactions. That means they can go in the forward direction or the reverse direction, depending on what is needed by our body. Chemical reactions can be, the rate of those reactions can be increased. In other words, they can speed up and go faster. If you raise the temperature, raise the concentration of the reactants, or the particle sizes are smaller. The smaller the particle sizes, the faster the reaction will occur. Like chewing up our food will digest it faster. All right, catalysts are substances that increase the rate of a chemical reaction. An enzyme is a biological catalyst, and it is almost always a protein. And that is it for section 2A. So we're going to get out of this section and go on to section 2B, which I should have already pulled up. Yes, okay. And section 2B will focus more on organic chemistry, including biochemistry, which is the study of chemical composition and reactions of living things, living matter. Now, all chemicals are either organic or inorganic. When you take chemistry at the college level, the first chemistries that you take are inorganic chemistry. And then you take organic chemistry, and after that, sometimes you will take biochemistry. Your inorganic chemicals are going to be chemicals that they might contain carbon. I know it says do not contain carbon, but they can contain carbon. They're just not going to also contain hydrogen. If they're organic, they contain carbon and also hydrogen. Okay, and it doesn't say that in the notes, so you may want to add that to your notes, that organic compounds contain carbon and hydrogen. And I'll write the symbols. Organic compounds are going to contain carbon and hydrogen. Okay, good. Not pretty, but at least I didn't mess up. So the inorganic compounds, examples would be water, any of your salts, your sodium chloride, and any other type of ionic compound, Many of your acids and bases are inorganic, although there are organic acids like citric acid that's found in fruit, lactic acid that builds up in your muscles when you exercise. But a lot of acids and bases are inorganic, like hydrochloric acid, which is stomach acid. And organic compounds are going to be in groups called carbohydrates, fats, or lipids, proteins, and nucleic acids. And they're going to contain, again, carbon, but also hydrogen, because carbon dioxide, or CO2, is not an organic compound. It is an inorganic compound because it only contains carbon and oxygen. It doesn't have hydrogen. All right, water is the most abundant inorganic compound. It accounts for, depending on how hydrated you are, and we all should probably be more hydrated, it accounts for 60 to 80% of the volume of living cells. It's the most important inorganic compound because of its properties. Because it's polar covalent, and it forms hydrogen bonds. Then it has the properties of high heat capacity. That means it has it holds in heat. It helps us maintain our body temperature, basically. It has a high heat of vaporization, and that means that when we sweat and water evaporates, it releases a lot of heat energy when it evaporates from the surface of our skin. It has polar solvent properties, so water can dissolve other polar covalent molecules, and it can also dissolve ionic compounds. Water is very reactive, and water provides cushioning in some of our joints, and some of our fluids. The property of water called high heat capacity is that water has the ability to prevent sudden changes in temperature. Think about how long it takes you to boil water, but the pot that you boil the water in gets hot really, really, really fast. But the water takes a while to change temperature. That's the high heat capacity of water. Water also has a high heat of vaporization, which is useful for cooling through sweat. Water is polar, so that makes it a good solvent for other polar molecules and ionic compounds. Polar and ionic will dissolve in water easily. This is showing you how sodium and chloride ions dissociate and dissolve in water. If you have a crystal of salt, the sodium ions will eventually become surrounded by water molecules, and since sodium has a positive charge, water will surround it with the oxygen end facing the sodium, because the oxygen end is negative. The oxygen is the red end, see? And then for the chloride, since the chloride ions are negative, water will surround chloride with the hydrogen ends, or positive ends, facing the chloride. So water forms these spheres of hydration around ions, and that is how water dissolves ionic compounds. Water is very reactive. It is a part of hydrolysis reactions or breakdown reactions. It is used as a reactant to break apart large molecules. And water is used in dehydration synthesis because it is formed as a product. And water, it has a function of cushioning. For example, CSF, cerebrospinal fluid, cushions the brain and the spine. Salts are ionic compounds that dissolve in water, and the ions that come from salts are called electrolytes. We have electrolytes called sodium, Na+, potassium, K+, calcium is Ca2+, iron, Fe, 2+ or 3+. So these are ions that form when salts dissolve in water in our body, and that the charged ions are now called electrolytes. Some of the common salts in our body besides sodium chloride are potassium carbonate. I'm so sorry. That is calcium carbonate, and potassium chloride, and also calcium phosphates are important salts in the body. Okay, acids and bases. can also form electrolytes in water because they ionize and dissociate in water. One example of an acid is hydrochloric acid, and it's going to dissolve or dissociate into, the cation will be H plus or hydrogen ion, and then the anion will be Cl minus or chloride ion. Acids are defined as proton donors because a hydrogen ion is simply a proton. So it donates hydrogen ions or protons in solution. A lot of times the chemical formula for an acid, as you can see here, will begin with H, and that's because it gives up that hydrogen when it dissolves in water. Okay. And bases are proton acceptors. They will pick up extra hydrogen ions from solution. Some important bases are bicarbonate ion and ammonia. All right, and this is where we'll start in the next lecture, is slide number 12. Slide number 12 of section 2B slides.